Hello everyone, welcome to the next video on equilibrium. Today we are going to solve some of the examples based on equilibrium problems. Basically there are two types of equilibrium problems. One is based on spheres and another one is based on strings. So today I am going to talk about some of the few examples based on sphere. Okay, before going to that, let me again discuss the previous, the last class slide, which says that when two planes, that is the plane 1 and plane 2, when two planes are forced which act exactly perpendicular to each other, when two planes act exactly perpendicular to each other, then if one plane which makes an angle theta with respect to horizontal, the same theta will form in the another plane with respect to vertical. This is what the important condition yesterday I stopped, right? So let's take the first problem. What is the first problem says? A sphere which weighing 100 Newton is fitted in a right angle notch as shown in figure. If all the contact surfaces are smooth, determine the reaction at the contact surface. Here you see they are given a sphere and which is having weighing around 100 Newton and is it fitted with a right angle notch. Notch means it is an opening which provided at the dams to allow the water to flow from the dam to the channels. Okay, and here they are asking us to determine the reaction at the contact surface. So we have to determine the unknowns which are present at the contact surface. So this is the problem that they have given. What is this problem says? You see here, they have given the two planes, that is the notch, the opening of the notch, which has been at an angle of 90 degree, which is right angle to each other. A sphere has been fitted here, which is having an weight of 100 Newton. Okay. Now, as we discussed yesterday, the first thing before solving any of the problem, we have to go with the procedure. First, we have to draw the free body diagram. Then we have to check whether we can apply the Lambies theorem or not. If not, we have to go for applying the equations of equilibrium. Then we have to resolve to get the unknowns. Here also, first step, what I am going to do here, I am going to do here with first drawing the free body diagram. How to draw the free body diagram? As I told, that free body diagram is that it's a diagrammatic representation of all the forces and movements which are acting at a particular body. Here you see, to draw the free body diagram, first I have isolated the body, that is I have written the sphere here, and I have written the two planes, that is the first plane and the second plane. The first plane, here you see in the problem, they have given that the first plane which is making an angle of, the first plane which is making an angle of 60 degree with respect to horizontal, right? If one plane which is making an angle of 60 degree with respect to horizontal, that is what I have written here. The first plane which is making an angle 60 degree with respect to horizontal. The second plane which is making an angle 30 degree with respect to horizontal. The second plane which is making an angle 30 degree with respect to horizontal. As we mentioned, to draw the free body diagram, first we have to write what are the forces which are acting in the system. So I have written the sphere. Then I know the one thing we have to remember while solving the equilibrium problems is that whenever there is a contact surface which exists in a body, then there should be always a development of the reaction at the particular surface, and the reaction will always develop normal to the contact surface. Okay, here you see the contact surface, there is A, which is at point A the sphere has been contacted, and at sphere B the force has been contacted. So wherever the contact surface will come, there we should definitely will get a reactional force from the contact surface. So these are the reactional force. So the first reactional force, that is RA, which is always acts normal to the contact surface. That is what I have written here, plane 2. And here at B, there is a one more reactional force, that is at the contact surface, which is developed and it is acting exactly perpendicular to the sphere. So here again I have written a perpendicular reactional force which is developed at point B. So which is denoted as RB. Now we know that there is a first plane which is acting here, and there is a reactional force at point A which is passing normal to the contact surface. So the angle made between both of them is 90 degree. As we discussed earlier in the condition that when two planes which acts perpendicular to each other, then if one plane which makes an angle theta, that is 60 degree with respect to horizontal, then the other plane, this is the another plane, that is RA, will make an angle of the same theta with respect to vertical. So what I have written here, I have written here the angle 60 degree which framed with respect to horizontal for the first plane. The same thing I have taken and I have written to RA with respect to 60 degree, that is with respect to vertical. The same way for the second one, that is RB, it is a reactional force developed at the contact surface B which is acting exactly perpendicular to this particular plane. So RB and the second plane which is framing a perpendicular, that is 90 degree. As we know that when two planes which acts exactly perpendicular to each other, then this particular plane which is making an angle theta with respect to horizontal which is 30 degree, then this force, the RB force, will make an angle of 30 degree with respect to vertical. So that is what I have written here, RB, which is making an angle of 30 degree with respect to vertical. So now it is clear that one thing we have to remember always, whenever there is a contact surface which exists in the body, then there will always a development of a reactional force at the contact surface. And the second thing is that whenever two planes meet perpendicular to each other, then if one plane makes an angle of theta with respect to horizontal, the same theta will form with respect to vertical on the another plane. So here we know about the free body diagram, right? Next thing what we have to do, after that we have to check for whether it is applicable to Lambies theorem or not. To check that whether it will be applicable to Lambies theorem or not, so what I am trying to do here, I am trying to do whether three forces are there or not. Here you see there are three forces which are acting in a system. This is what the free body diagram of the figure, that is I have represented RB here, RA which is acting at a point, this point, if I represent that as O, this is O point from O which is acting like this, and there is a self weight of the sphere. The self weight of the sphere they have given as 100 Newton. So 100 Newton is the self weight of the particular sphere, that is I have represented here. Now three forces are acting at a point, so the Lambies theorem can be applied. All right. Next one, what we have to do, we know that what is Lambies theorem. Lambies theorem is the theorem where if three forces which are acting at a point, then if the one force is directly proportional to sine of the angle between the other two forces. So what is the first force here? The first force, if I taken RA as the first force, then if this is the force, then the total angle framed by other two forces are this one, the opposite angle. So RA by the total angle is 60 degree plus 90 degree, that is 150 degree. So RA by sine of 150 degree, which is equal to 100 by, what is this opposite angle? This opposite angle is 90 degree. That is we have already determined. So 90 degree. Then which is equal to RB by total, which is 120 degree. So RB by 120 degree. So this is what which indicates, that is RB by sine of 120 which is equal to RA by sine of 150 which is equal to 100 by sine 90. Now equate any of the two equations with the one unknown parameter. First, if you equate RA with respect RA by sine 150 which is equal to 100 by sine 90, then we will get RA equal to 50 Newton. The same way you equate RB with respect to the 100 Newton, that is if you equate these two, we will get RB equal to 86.602. Newton. Okay, this is are the two unknowns which have been found in the particular problem, right? The same way, it take down the next problem. What next problem says that a smooth circular cylinder which is having a radius of 1.5 meter is lying in a triangular groove, one side of which makes an angle of 15-degree angle and the other which makes an angle of 40-degree with horizontal. Find the reaction at the surface of contact if there is no friction and the cylinder weighs around 100 Newton. These problems look similar to the previous problem. Here they are saying that circular a smooth circular cylinder has been rested on a triangular groove which having a radius of 1.5 meters, right? And it is rested with the triangular groove having one side with 40-degree with respect to horizontal and the other side is 15-degree with respect to horizontal. So first what we have to do, first we have to draw the free body diagram. As I mentioned earlier, when two planes, as we know that before drawing the free body diagram, first I want to isolate the body. If you isolate the body, that is, first write down the sphere, then write down it is rested with two planes. One is making an angle 40-degree and another one making an angle 15-degree, right? One is 15-degree and another one is 40-degree. Now after isolate the body, we know that the self weight of this particular sphere is 100 Newton. So I've written 100 Newton here. Next, here there are two planes. We know when there is a contact surface existed between the sphere, then definitely there will be the reactional force which will develop at the contact surface and it is always acting normal to the plane. That is here, that is which is at B point, so it is RB. And also at A point, there is a contact surface, so there is a development of one more reactional force, that is RA. So what will happen when two planes, this is the first plane and this is the second plane which meet exactly perpendicular to each other, then if one plane which making an angle theta with respect to this horizontal, then the same theta will form with respect to vertical. If you look at the free body diagram here, that is I have written at the left corner, you see here, so we have written the free body diagram of the sphere. Right, so it is the A point and this is the B point. In A point there is a contact surface where the body is acting. So when there is a contact surface, there is a development of a reactional force which is acting along this direction. And there is at B point there is one more reactional force which is acting along this direction. Now we know that if this plane which is making an angle theta with respect to horizontal, the same theta will form in this plane, that is with respect to vertical. So RA is making an angle with theta with respect to vertical. So RA, here you see the force diagram I have written, RA is making an angle the same 15-degree with respect to vertical. The same way here at RB, the reactional force, and there is a plane, the plane which is making an angle 40-degree with respect to horizontal, the same theta 40-degree will forming the reactional force with respect to vertical. So here you see the RB has been written like this with an angle of 40-degree with respect to vertical. And there is a self weight of the sphere, so it is 100 Newton. So 100 Newton has been represented here. Now after we draw the free body diagram, what we should do, we should check for whether it is applicable for Lambies theorem or not. Here there is only presence of three forces which are acting at a particular point, so we can easily go for applying the Lambies theorem by knowing one force at least. So here we know the one force magnitude as 100 Newton and all the other angles. So how to apply the Lambies theorem? If three forces are acting at a point, then the one force is directly proportional to sine of the angle between the other two forces. If I consider the first one, that is 100 Newton, which is acting downward, if that is the first force, the angle made by the other two forces are 40-degree plus 15-degree, so 55-degree. And this is, what is the angle here? The angle here is, that is 90-degree from here to here, plus the remaining is 50 degree. So totally 140 degree here. And the same way, what is the angle here? Total angle is 180 degree. Out of 180 degree, if you deduct the 15 degree, total we will get 165 degree. So if you apply the Lambies theorem, RB by sine of 165 degree plus RA by sine of 140 degree, which is equal to 100 by sine of 55 degree. That is what has been written here. By after writing the Lambies theorem, you see here 180 minus 40 RB, which is equal to sine of 180 minus 15 degree, 100 by sine of 55 degree. So after you written the Lambies theorem, equate the unknown reactional force to the known force, then you can easily get what is RA and RB. Okay, RA value will get 78.5 Newton and RB will get 31.6 Newton. Okay, next one, if you moves on to the next problem, what is the next problem says? A horizontal channel with an inner clearance. The inner space is available in a horizontal channel which is 1000 mm, which carries two spheres, which is having a radius of 350 mm and 250 mm, and whose weights are 500 Newton and 400 Newton respectively. Find the reaction at all the points of contact. So here the problem says that a horizontal channel is there which is having an inside clearance of 1000 mm, which has been fitted with two spheres, which is one is having a radius of 350 mm and another one is having a radius of 250 mm. That has been shown in figure with their weighing of 500 Newton and 400 Newton respectively. They are asking us to calculate what is the what is the unknown force at the contact surface. What are the contact surface? This is the contact surface 1, this is the another contact surface 2, that is B, and C as well as D. Right? To solve the problem, what is the basic thing we require? We require to draw, first thing we require to draw what is the free body diagram of the question. To draw the free body diagram, one thing I want to know, what is the direction of the forces which are acting. Right? Example, here they have given the two spheres. The two spheres, if one sphere is having some self weight and it is acted to this, sphere 2 is acting to sphere 1, and sphere 2 is also touched with the wall at a D point, and there is a self weight, and also there is a reaction which is developed at the C point. But I didn't know what is the angle which is there from the reactional force which is acting at B. So first what I want to do before drawing the free body diagram, I want to determine what is the direction of the reactional force at B. Right? To determine what is the directional force at this particular point B, so let me consider this particular geometry. Here you see what we have done. We have written the same problem here with the all the geometrical notation. Here you see, we know that there are two spheres are there. The first sphere which is having a radius of 250 mm and the second one which is having a radius of 350 mm, and the total inner clearance is 1000 mm. Right? So this is the 1000 mm. So what I want to know, I want to know what is the angle made by the reactional force which is acting at B from the second sphere to first sphere, and also I want to know what is the reaction which developed from sphere 1 to sphere 2. So to know the reactional force at S1 and S2, I want to know what is the direction of the force. To calculate that, I want to know this theta. How to know this theta? Draw a horizontal line, that is an inclined line which joining the both the radius, right? And also form a triangle, a rectangle triangle here. So to calculate the theta, at least I has to know two sides. I know that this is the hypotenuse side of the theta, which is equal to the radius of the two sphere. This is the radius of the second sphere, that is S2, which is equal to 350, plus the radius of the sphere 1, which is equal to 250. So totally which is equal to the 600. What is the 600? The side S2 and S1 which is measured with the distance of 600. Okay. Same way I want to know the another one side. What is the another one side? That is, either I want to know what is S2E or I want to know what is S1 into E. So I can easily get what is S2 into E because the total inner clearances they have already given it is 1000 mm, out of which the radius of the second sphere, which is 350 mm, the radius of the first sphere is 250 mm. You deduct these two part. What is 350 mm minus 250 mm? The remaining is 400. So what is it that 400 indicates? 400 indicates this particular distance. So this is called the horizontal distance, and this is the hypotenuse distance. Now we have hypotenuse distance and horizontal distance. So I can easily define the cos theta. If you define the cos theta, the angle you see here, I have explained it here. That is S2 into E, which is equal to 1000 mm, minus 350 minus 250, which is equal to 400 mm, and S1 into S2, that is the diagonal line which representing the both the radius of the spheres, which is equal to 600 mm. So the theta between the reactional force which is acting from S2 sphere to S1 sphere and S1 sphere to S2 sphere, which is making an angle of 48.19 degree with respect to horizontal. So after I determine the direction, next what I want to do, I want to go for what is the free body diagram of the sphere. So here I have represented the free body diagram of both the sphere. Here you see I have written the free body diagram of the sphere 2, which is having a self weight of 500 Newton, and there is a reactional force which is acting from sphere 1 to sphere 2 at the point of contact B, right? At the point of contact B, there is a reaction from the sphere 1 to sphere 2. That is how written it as RB. Next, the same way, in sphere 2, there is also one more reaction which is developed from the wall. At the side of the wall, that is RD, which is a reactional force which is developed towards the rightward direction that I have indicated here. And also, at the base of the sphere 2, there is a one more force, reactional force, which is developed, which is acting upward. Here you see, I will show in the diagram. You see here, this is the diagram where we can see there is at point D, there is a contact surface. So there is a one reactional force. Here another contact surface. So one more reactional force. And here from S1 to S2, there is a one more contact surface and there is a self-weight. These are all the forces we have written here in sphere 1, right? The same way we can write the free body diagram for sphere 1, which mentions that first one is the self weight of the sphere 1 and a reaction from S2 to S1, which is acting upwards. So that is here we have written RB, and then from the side of the wall to towards the leftward direction. That is here you can see here you can see it is moving from this particular direction. So there is a one more force which is acting. So these are the two reactional forces and free body diagram of the spheres have been written. So next thing I want to see, I want to check for whether it's applicable for Lambies theorem or not. So here you see in the free body diagram of first one, there are four forces are acting: 500 Newton, RD, RB as well as RC. So as we know, Lambies theorem can be applied for only three forces when are acting at a same point. So for sphere 1, we can't apply the Lambies theorem. We can solve this particular problem by using Lambies theorem that I have been shown in another solution. We'll look at it later. So here, so I can't apply the Lambies theorem. So what I did, I directly apply the equations of equilibrium. What is the equations of equilibrium? That is summation of H equal to 0 and summation of V equal to 0. Then if you resolve the forces vertically and horizontally, if you resolve the force vertically, what are the vertical force? That is, one is the 500 Newton acting downwards, so which is equal to minus 500 plus a RC which is acting upward, so plus RC, and there is a inclined force RB which is acting with respect to horizontal of 48.19 degree. So therefore RB sine 48.19 degree is the one more vertical component. So same way resolve the forces into horizontal component and vertical component. Here you see, if you resolve the horizontal component and vertical component, RC minus 500 minus the value of RB into sine 48.19 degree. The same way we have to resolve for horizontal, summation of H equal to 0, which indicating that RD minus RB into cos 48.19 degree, which is equal to 0. Same way we have applied the equations of equilibrium for the second sphere also. If you apply summation of H equal to 0, what are the H? That is RB, which is acting at an angle of 48.19 degree. So RB into cos 48.19 degree, it is a positive force because moving towards the rightward direction. Next, minus RA. What is RA? RA is a leftward force which is acting towards the leftward direction. So RB cos 48.19 degree minus the 400, which is equal to 0. So here they have resolved it with respect to vertically, that is RB sine 48.19 minus 400, which is equal to 0. They will easily get what is RB value. If you get the RB value, then you can easily substitute the value of RB for all the equations wherever you will get RB. So if you resolve the same forces with respect to horizontally, we'll get minus RA because it is moving towards leftward direction plus RB cos 48.19 degree, which is equal to 0. So RA equal to, we'll get 357.77. If you substitute the value you obtained from the sphere 1 to wherever it is applicable for sphere 2, then we'll get the RD value as 357.77 and the RC value as 900 Newton. As I mentioned earlier, we can also solve this problem by using, what? Lambies theorem. What is Lambies theorem says? Which says that when only three forces are acting at a point. So in sphere 2, what happened? Basically, there were 4 forces. Now what I have done here, I have taken the RC in the sphere. Actually, the sphere was like this. The RC force, which is acting upwards, and 500 Newton was acting downwards, and there is a rightward force RD, and there is a left, that is inclined force RB was acting. So what I have done, I have used the resolution of force here. So I know the 500 Newton is acting downward, so it is, I have taken as minus 500 plus the RC is acting upward, so I have taken it as positive force, that is RC minus 500. So totally how much forces are acting here? There is only 3 forces which are acting in a system, and we have determined the angle in between all these forces. So now if you apply the Lambies theorem for the same problem, you see here RC minus 500 by sine of 131.81 degree. What is sine of 131.81 degree? Which is equal to the RB reactional force, which makes an angle 48.19 degree with respect to horizontal. So what is the remaining angle? The remaining angle is 41.81 degree. So the remaining angle from here to here is 90 degree plus 41.81 degree. So totally 131.81, and here it is remaining is 48.19 degree plus 90 degree. So it is 138.19 degree. So you can equate as we proceed in the previous problem, that is RC minus 500 by sine of 131.81 degree, RB by sine of 90 degree, which is equal to RD by sine of 138.19 degree. So if we equate the known force with the unknown force, we can easily get what is the unknown forces, right? So here they have applied the same Lambies theorem for sphere 1. We know the sphere 1, which is having a weight of 400 Newton. So if you equate the equation, we can easily get the unknown forces. Okay, that is what it says. Okay, next one. So what is the next problem? Next problem which says that the two identical spheres which are acting, which are weighing around 200 Newton, are placed in a trough as shown in figure. Assuming all the contact surfaces are smooth, find the reactions developed at the contact surface A, B, C, D. Here they have given the two identical sphere which weighing around 200 Newton, which are placed at a trough as shown in a figure. Assume all the contact surfaces are smooth, determine the reaction developed at the contact surface A, B, C and D point. Here you see what is the problem they are given. There are two rollers which are present, which are rested on a inclined plane, which is inclined at an angle of 30 degree. So what I have to do, I want to draw the free body diagram for the particular problem or particular sphere. Here you see the first sphere I have considered here, which is inclined with an angle of 30 degree with respect to the plane. So that is we have written here. And there is a contact surface at point B and point A, and also there is a self-weight. You see here at point A, there is a contact surface which is, so therefore should be a development of a reactional force along this direction. And at B, there is a contact surface with roller 2, so there will be one more reactional force which is acting like this. And there is also a one more, the self weight which is acting downwards, right? So what we have to do, we have to draw the free body diagram like this. So here from the free body diagram, what I can say, from the free body diagram, I can say that the downward force, which is having an angle, which is having a self weight, and there is a reaction from B and there is a reaction from A. We know when the two planes are which are acting perpendicular to each other, then one plane making an angle 30 degree with respect to horizontal, the same angle will form with respect to vertical. Okay, now you can use the Lambies theorem or you can use the equations of equilibrium, no problem, anything you can use here. So resolving the forces horizontally, that is summation of H equal to 0. So I am getting RB minus RB cos 30 degree. Here you see, here if I resolve the force into two components, that is horizontal force and the vertical force. So the horizontal component is RB cos 30 degree, it is moving towards the rightward. So it is a positive force minus RA force. If I resolve the RA force, it is looks like this. So there is the force, the horizontal force, which is moving towards the leftward direction. So what will happen, which is equal to RA into sine 30 degree, which is why it is 30 degree, because this force which is making an angle with respect to vertical, therefore the horizontal component is sine theta, so which is equal to RA sine 30 degree. Okay, the same way you resolve it for the vertical force, that is summation of V equal to 0. Then from equation 1 and 2 we can easily get what is the unknown RB and RA value. Okay, after you obtain that, then apply the same free body diagram for the another sphere or another roller. The free body diagram of the roller appears like this. That is the self weight as 200 Newton is acting downwards, and there is a contact surface at C, and there is a contact surface from the vertical wall at point D. So there is again there is a presence of one more reactional force. If you draw the free body diagram, how it looks, it will looks like this. There is a sphere. For the sphere, one self weight which is acting downwards, and at point C there is the reactional force which is acting in this particular direction, and at D there is one more a horizontal reactional force which is acting along this direction. So if you resolve the components, you can determine the angle. Then if you resolve it, what we will get, if you resolve with respect to vertical, we'll get minus 200, that is the downward force which is acting, plus RC. If I resolve the RC component, how it will look, it will look like this. So RC cos 30 degree minus 100 sine 30 degree. What is 100 here? The 100 is the value we have obtained for RB. So minus 100 sine 30 degrees. So we'll get RC value as 288.68. The same you resolve the force for horizontal. So you will get the value of RD as 230.94 Newton. So RA is 173 Newton, RB is 100 Newton, RC is 288.68 Newton, and RD is 230.94 Newton. In the next lecture, we'll be talking about the problems on equilibrium which based on the string. Okay, thank you.